Hi students, the topic of this video is conservation of energy, which is chapter 8.3 in the section of force and motion. So the learning objectives for this topic is to state the law of conservation of energy, to discuss the interconversion of PE and KE with consideration of energy loss, and also to solve problems involving conservation of energy. So last time we have talked about the KE and PE, and this time we're going to talk about how they are interconvert with each other, which means that KE could be converted to PE and PE could be converted to KE, and also there could be energy loss in our reality. Let's start this topic with law of conservation of energy. I'm pretty sure that you have learned, or at least you have seen this in the, I think it's in the heat capacity. You have seen this before, and it's the same. Energy can change from one form to another, but it cannot be created or destroyed, which means that you cannot just create some energy by yourself, or you cannot just destroy the energy by yourself. Energy can only be converted, can only be changed from a form to another. So now, before we go deeply to this, let's use some very easy example or easy illustration to introduce what does it mean by conservation of energy. There could be two cases. We define the first case as without mechanical energy loss, which means that the total mechanical energy remains unchanged. When we talk about the total mechanical energy here, we talk about the total mechanical energy of this block only, and where this block is sliding down a smooth slope. So if it's smooth surface, then there is no friction when this block is moving, and this is initial level, which means that initially this block is here, and the initial velocity is 0. But after when it's sliding down, then it accelerates, so that the final velocity for this block is not 0. And this is the reference level here. So when this is the reference level, which means that the potential energy at this level is 0. So initially, it's not moving. So KE is 0. KE here is 0. And then, when it's moving, after it moves for displacement and it arrives here, then the velocity is not 0. So that the final KE is not 0. And let's have a look at the PE. The PE, if originally the PE is 6 here, its arbitrary value is, if it is 6 or initially, then because it's being displaced with a height, that means it moves vertically downward. So as the height change here, then it lose PE. It lose PE because it is moved to a lower position. So you can see the comparison for the KE and also the PE before and after. Another case would be with mechanical energy loss. So because the surface now it has friction, so when it moves, some of the energy would be lost due to the friction. It's the work done against friction. So the lost mechanical energy here is converted into other forms of energy. Remember, they did not disappear. They are not destroyed, but they are converted into other forms of energy. Taking all forms of energy into account, which means that we consider all the energy. We also consider the energy lost due to friction. Then the total energy of this system actually is always conserved. What does it mean by system here? Is consider the KE/PE of this block and also the energy lost due to friction, then it's always conserved. They are not destroyed. And the initial KE and initial PE of this block, which would be equals to the final KE and final, and this should be PE, sorry for typo, this should be PE. They would be the same if we also consider the energy lost, which means that the final PE and final KE should be smaller than the initial KE plus initial PE, because some of the energy here is changed, is converted to the energy loss due to friction here. So the sum for this part is equal to the sum of this. And taking the example again, sliding down a smooth slope, this time is not rough. Then the initial PE would be like this, and because it's not moving initially, so the KE is zero, and there's no energy loss initially because it's not moving. And the final state after it moves through a displacement with friction, and the PE of course is reduced because it's the vertical position of this block is reduced, is lowered, and the KE increase because it accelerates. So the KE increase, the velocity changed from 0 to non-zero. But you see, initially the mechanical energy is greater than the final mechanical energy of this block because some of the energy is lost due to friction. So some work is done against friction. So the total mechanical energy of the block is lost due to this friction. But the total energy here, considering all the energy above, should be the same for the final stage. The final state should be the same as the initial state. And we used car braking, which is very usual and typical in the daily life, as an example to illustrate energy conservation. Initially, it's moving, but after you apply the brake, then finally it stops. And initially, we define initial PE should be like 2 here. Then because it is not lift or lowered with a height, so the PE remain constant, is not changing at all. But the KE is initially moving, so there should be some KE here for the car. And at the end it stops, so the KE here is 0. Let's have a look about at the PE and KE. PE plus KE is the mechanical energy, and here you can see that why the total mechanical energy is reduced comparing the final state and the initial state. It should be the same, right? Because when you apply a brake on this car and when it decelerates, actually energy is lost due to friction. So that the mechanical energy of the car is not constant because the energy is lost due to friction. And this time the energy, the work done against friction, it could be converted into like heat or sound. But if we consider all the energy here, then it should be the same. Initially and finally, it should be the same. And the last part of this video, I would like to introduce this example 1 to you. Let's work on this example. It's also an example of car braking where a car of 2000 kg mass moving along a horizontal road. You see the velocity is not meter per second. This time is 54 kilometer per hour. It's 54 km per hour, and it brakes suddenly. So the average friction acting on the car is 12,000 Newton. And it asks for the distance d traveled by the car before it stops. So for part A here, part A is talking about this example, just a horizontal road. And the solution, how to do it. The work done against something would be the loss in Ke. And the loss in Ke is the work done against friction. It's against friction. And then how can we use this relation to find the distance? We use the energy conservation, which means that here work done against friction, which should be Fd. The F is the friction, one is 12,000, and the D is unknown. So let's write down 12,000 D equals to the loss in Ke here. And you know that it stops at the final state, so that the velocity would be 0. The final V is 0. So the loss in Ke, you can just write down the initial Ke, which is 1 over 2 mv squared, and the m is here, the mass is 2000. And then the initial velocity is 54 km per hour. Then this time we need to convert the unit by dividing it by 3.6 and then square. So you use the calculator to calculate the D, and the answer would be 18.75 meter. It is an exact value. So if you want to take freeze effect, and it's okay, which will become 18.8 meter. It's acceptable. And then the second part of this question is, this time we change it. Suppose the car brakes when it moves down a slope. This time with inclination here, it's not a horizontal surface anymore. And all the things is unchanged. We just change the horizontal road to a slope with inclination. So this time, how does the distance traveled change? We don't need to calculate the value because we don't have the angle here. We only need to state how would it change. So when the car moves down the slope before it stops, apart from the loss in Ke, think about it, it also moves with a vertical displacement. So as the height is reduced, that means there is also a loss in the gravitational Pe. We just write down Pe here. What would be equal to the sum of the loss in both Ke and Pe, which would be, again, would be the work done against friction. And because we don't have enough space, I just write down the symbol for friction, and you can write down friction in your notes. The work done against friction is equal to the sum of the loss in Ke and Pe. And because you also need energy, you also need the work done for this loss in Pe, and not just the loss in Ke. Therefore, you should need a longer distance for the car to travel before it stops, because you need to also compensate like the loss in Ke and loss in Pe. The last thing I would like to talk about is the energy analysis. We are doing some kind of energy analysis throughout the conservation of energy. And if you look at it carefully, I only consider initial state and final state, which means that the process between the initial state and final state, we do not consider. The motion in between is not involved in our analysis. So every time it's just like considering u and v. We consider this, and also the initial height position and final position. In between, we don't consider it. So this is how we deal with the questions regarding energy conservation.